This video is a further discussion of the video Flying Saucer Engine, which appears on this website, www.newrelativity.net. That video comes from the article Magnetic Force Engine, also on the website. The key component in those discussions is a permanent magnet that rotates about an axis. This video will examine some of the points of interest generated by those discussions. Figure 1 is a brief illustration of the principle involved. A magnet shown as a dashed line rotates into a position shown as a solid line. At the instant the magnet is in the solid line position, it begins to establish its magnetic field in this new position, because this field would be different than the field of the magnet when it was in the dashed line position. Since nothing can move faster than the speed of light, this new position field expands outward from the magnet at the speed of light, which is shown by the magnetic field lines expanding outward at the speed of light. Figure 2 shows a typical magnet with some field lines sketched in around it. Note that one field line is labeled with a star and is drawn straight out of the center of the magnet. Since all field lines are curved in reality, this line must have a slight curvature, but it is drawn straight for the convenience of this discussion. Figure 3 defines some simple parameters used to examine rotating magnetic fields. Dimension r is the magnet radius as the magnet spins around its central axis. The magnetic field extends beyond r, and Figure 3 uses multiples of r, as shown, to locate some of the positions within the magnetic field. Velocity v is the tangential velocity of the magnet radius, so multiples of v describe the velocities of points out in the magnetic field. The angular rotation speed of the magnet is omega. We know from relativity that the peripheral speed of the magnet face at r cannot exceed the speed of light. But now we must address the tangential speed of the magnetic field beyond r. The standard understanding of relativity is that nothing can go faster than the speed of light. So do we assume that this also applies to the magnetic field of the spinning magnet? A possible answer to this question is shown in Figure 4, where the peripheral speed of the magnet is some fraction of the speed of light, c, say 1/2 c. This means the magnetic field would eventually exceed c as you travel outward from the magnet. If we require that the field speed will not exceed the speed of light, the radial line star would approach the curved line shown. The equation of this line is alpha equals delta t times the quantity omega minus c over r, where alpha is the angle to the position of the curved magnetic field line, and delta t is the amount of time that has passed after the magnet had rotated into position. This assumes the magnet keeps rotating after it achieves the position. This equation describes a field line that is moving at speed c while it is trying to follow the magnet rotation. The angle alpha exists between the true circumferential position of the field and the geometric axis of the magnet, illustrated by the dashed line. As the magnet continues to spin, the field would wind around the magnet over and over again, eventually looking like a spiral-wound clock spring. We now go to Figure 5, which shows the experiment of Figure 4, but viewed by an observer at a position 2r from the magnet's center and traveling by the experiment at a speed approaching c. To this observer, the peripheral speed of the field at this point is 0. So what shape does the magnetic field have in this case? Does this new observer compute angle alpha to be the same as an observer stationary with respect to the magnetic rotation axis? While thinking about the experiments of figures 4 and 5, let's consider the experiment of figure 6. This experiment shows two non-magnetic masses connected by a pole. The masses are identical and rotate about an axis at the center of mass of the assembly. This experiment is obviously parallel to the experiment with the magnets, but now it is a gravitational field which has the potential to exceed the speed of light. You could also design a similar experiment using electrostatic fields. Although it is easy to do the simplified analysis of the flying saucer engine as presented in that video, a detailed study is much harder. Of course, the magnetic force engine would not work, and the law of conservation of momentum would not be in question if magnetic fields instantly rotated into position and exceeded the speed of light. The purpose of this discussion is not to say that these puzzles can't be solved or that relativity is invalid. In fact, the goal here is to begin to say how these puzzles can be solved. Naturally, relativity will be one of the tools used to do that, but new approaches may be needed within relativity theory.